Great, thank you. I'm happy to be here today, and I guess virtually here today. And I just wanted to thank all the conference organizers for giving me the opportunity to talk and present to all of you, and to be able to hear what's been a really great collection of talks over the past few days. I've learned quite a lot, and it's been great to have the opportunity to hear from people I otherwise wouldn't have been able to without this conference. So my name is Andrew Emerick. I'm currently a Pasadena postdoctoral fellow in theoretical astrophysics, jointly appointed at Carnegie Observatories and Caltech. And what I wanted to do today was introduce to all of you a set of simulations that are currently running that I am very excited about, and my collaborators and I are both very excited about. But as these simulations are sort of still very much ongoing, just as a warning, this will be a mostly results-free talk, but I promise there's still cool images and a movie at the end if you stick through. So my main motivation for carrying out the simulations I'm going to introduce to you is a little bit of a departure, I think, from what most people have talked about so far at this conference. So I'm mostly interested in trying to understand what the detailed chemical fingerprints are of the very first galaxies in the universe, and how we can possibly try to understand the origin of those fingerprints and how they map to observed stellar abundance patterns in galaxies in the local universe. So it's a bit of a departure because it's sort of the near-far connection and focuses on stellar abundances, but I think it's really important and well connected to what a lot of people here find interesting, because in order to understand this, you really have to have a good detailed understanding of the metal history and evolution of metal enrichment in the universe from the very first stars through ionization until today. And so in detail, again, the questions I'm interested in are, how are the stellar abundances of local group dwarf galaxies potentially representative of the very first galaxies? Or is it the case that the very first galaxies and their chemical signatures are better represented in stars and in Milky Way halo? And by understanding what those signatures are, can we know, which stars in the Milky Way or again the local group are remnants from the very first structures in the universe? And again, related to that, what are the signatures, unique signatures of stars formed directly from POP3 star enrichment, or most purely from POP3 star enrichment, and from both core collapse supernovae from population 3 stars and pair-instability supernovae from these stars. And in general, what physics really drives the mixing and evolution of metals in gas in the ISM, CGM, and the IAGM at high redshifts, and how does that play into driving the scatter and observed stellar abundances? And part of the reason why I'm so interested in doing this is because I think you can think of metals as nature's tracer particles, and so this is sort of illustrating that to some degree. This is a plot of the magnesium to iron ratio as a function of metallicity. And I see now I've conveniently lopped off the units or the numbers on the x-axis, but I think the point is still a bit clear, which is that there are differences in how and what stellar abundances look like in different galaxies. Shown here, you can see in color the different dwarf galaxies in the local group as the gray points, the stars in the Milky Way halo itself. And encoded deeply in these stellar abundances in both the median evolution of these abundances and in the scatter of these abundances, I think is a lot of details about galactic evolution to drive both the median trends here and the scatter in these abundances. And so it'd be particularly useful and exciting if we could take the observed stellar abundance patterns that we see today to learn something about the evolution of the first galaxies. And with these simulations, I'd like to be able to attempt to make that connection and do a lot of other interesting science with that as well. But part of the problem here, just to illustrate this, is that galactic chemical evolution is quite messy. So this plot shows an example of this with the sort of the median metallicity evolution of 3 different dwarf galaxies at high redshift with 3 different star formation histories, shown as the solid line, and then the scatter about that median in the shade line, and then the dots represent the stars formed in those galaxies. And the point is that depending on the star formation history of galaxies, depending on the local environment, the properties of gas, and all the feedback physics that you include in these simulations that could drive very significant differences in the median trends and the scatter and evolution in the metal content of these galaxies. And that's true for the total metallicity, but I'm also very interested in how that is true independently for individual metal species, which may originate from different nucleosynthetic sources like stellar winds or core collapse supernovae, type 1a supernovae, AGB winds, and our process enrichment as well. And so, with all that in the context, again, the questions I'm most interested in, which I think are broadly interesting to other people as well, I hope, are, what are the chemical fingerprints of the first galaxies? How is the gas from these first galaxies, the ISM and the CGM around them, and also the IGM, enriched in the early universe? And again, what drives the variety of stellar abundance patterns seen in galaxies today, both the scatter and spread within an individual galaxy, and also the galaxy-to-galaxy scatter, particularly for the very, very low mass dwarf galaxies that we see today. And what are the unique observable signatures of both POP3 and POP2 enrichment at high redshift? And so what I wanted to introduce to you today is what is, to my knowledge, I think, someone please correct me, is the first star-by-star cosmological simulations of the first galaxies for both POP3 and POP2 star formation. And so these simulations are ongoing, and they're run using the adaptive mesh refinement code ENSO. And again, they're first set of cosmological simulations where we do a star-by-star approach, which allows us to get detailed stellar feedback and detailed galactic chemical evolution from these galaxies. And this image here, which I'll sort of explain more later, is just a teaser of the simulation that's currently ongoing. I happen to pick redshift 19 for this image because that happens to be where the simulation is now. But what you're seeing here is just the full box projections of the gas number density on the left and the gas temperature on the right, overlaid in both cases with the oxygen enrichment on the left from the POP3 stars, which are shown as black points, and also the ionizing heating from these stars as I do follow full radiative transfer in these simulations. And so the gory details of this is that we have star formation with POP3 and POP2 stars. So we're following POP3 stars from 1 to 300 solar masses individually, randomly sampling an IMF with a characteristic mass of about 20 solar masses. And above metallicity threshold, which is driven by the carbon and iron abundance in the gas, we can form POP2 stars, which are again sampled randomly from an IMF. And followed individually for stars between 2 and 120 solar masses. And below 2 solar masses, I'd sort of aggregate the stars together into a single star particle, mostly because we only plan to run these simulations to about redshift 7, which is less than the lifetime of one of those stars. And we fold that in with a Grackle non-equilibrium chemistry and cooling, with a UV background, an updated Lyman-Werner background, and a self-shielding model of the gas against the UV background. And with the individual stars, we can do star-by-star multi-channel stellar feedback. So for each of the stars, we're tracking their evolution and whether or not they explode as core collapse supernovae. For the low-mass stars, we actually evolve them into white dwarfs and have a sort of a realistic way of capturing them as type 1a supernovae. And in the POP3 stars, we have both core collapse supernovae and pair-instability supernovae from the high-mass POP3 stars. For everything, we have stellar winds with a sort of reduced velocity approximation to make the computation a bit easier, and AGB winds from low mass stars. And I think what's most exciting and relevant, again, for the area of reionization is that we're also including ionizing radiation tracked with an adaptive ray tracing radiative transfer method for both hydrogen and helium. And on top of that, using an optically thin approximation, we're following Lyman-Werner, FUV, IR, and optical radiation from these stars. And what I'm most excited by, and I'm almost done, is that we're tracking, in addition to all the feedback physics, 10 different individual metal species, tracking different nucleosynthetic sources from all of these stars, having individual metal tracers for all these metal species, and a separate set of metal tracers for all these species, tracking the contribution to these fields from POP3 stars themselves, for a total source of 29 metal tracer fields, because we also include tracers for each individual source, like supernovae, POP3 core collapse supernovae, POP3 pair-instability supernovae, and a type 1a model with 4 distinct sources to try and distinguish between origins of different type 1a elements. And in addition to this, an R process model for R process enrichment. And almost last slide. So the full box, we have a fiducial simulation set with the full box simulations of a co-moving megaparsec run to about 0.5 to 1 parsec resolution of the finest cells, run with and without pair-instability supernovae. And then we will have a higher resolution zoom-in simulations following individual dwarf galaxies with different virial masses. And so with that, I will leave you with the cool movie of the simulation so far, and happy to take questions. Thank you.
Questions for Andrew. Sarah Bozeman asks, what assumptions are you making for the population 3 and population 2 IMFs, and do they have metallicity dependence?
Good question. So the POP3 IMF, here, so in both cases, the IMF is not metallicity dependent. For the POP3 IMF, we just assume an exponential IMF below a characteristic mass of 20 solar masses and a saltpeter IMF above that. For the POP2 IMF, we just assume a Krupa IMF.
Other question. Okay, Gerald Melima, why do you select these 10 elements to include?
It's a great question. So we try to, ultimately, right, we're limited into the number of elements we can follow because it gets expensive, both in sense of memory. So these 10 elements was the sort of the best, the most we could do with as few elements as possible, if that makes sense. So they track different yield sources quite well. So there's, for example, barium and strontium we picked because they're good tracers of the S process and also a little bit of the R process. We have different elements from the alpha elements like magnesium and oxygen from quark collapse supernovae, iron from type 1a supernovae, and also carbon and nitrogen, which are sampled from a bunch of these sources. And also, the elements we picked are generally those that are most well observed in either stellar abundances or in gas phase abundances.
Anna Schauer says, very nice talk, and I look forward to the results. Did you consider initial conditions with a non-zero streaming velocity?
Good question. We have not, mostly for the sake of simplicity. But I think, yeah, after listening to your talk, that's clearly something we should consider.
Okay, and Tom Tunes, since you simulate star by star, how does the IMF enter? Do you randomly sample from it?
Yeah, so the IMF, we assume an IMF, and then when a gas cell hits the right star formation criteria, then we randomly sample the IMF and deposit individual stars. So in many ways, it's the star formation routine works the way that anyone's star formation routine works, and IMF assumptions work. It's just that instead of a simple stellar population, we actually break that simple stellar population into individual stars in the simulation.
Okay, and Stephen McCandless, is the H2 rotational vibrational population fixed at thermal, or is it affected by the FUV pumping?
It is not affected by the FUV pumping. No, that is not something we include.
Okay, and I think we have time for maybe one last one. Dan Coe, you said no results yet, but anything preliminary? When did the first population 3, population 2 stars form? Any redshift 19 galaxies to speak of?
So you're looking at all the results that I have right now as I made this movie this morning. So it looks like the first stars in this box were forming at around redshift of 23, 24. I have not run any sort of halo finders on this yet to see exactly where they're forming and what kind of properties the dark matter and the gas are in those regions yet.